Welcome to our super short video lecture on intermolecular forces. Our essential understanding for today is that physical properties of molecular substances result from different types of forces between their molecules. It's a lot of words. Physical properties, we're looking a lot today at boiling point, though we might talk a little bit about melting point as well, but mostly boiling point. Molecular substances, we're talking about things that are covalently bonded. So covalently bonded molecules. And then these different types of forces between their molecules, these are what we call IMFs, or intermolecular forces, IMF. Our objectives for today are all about these IMF things. So we're going to define what even are intermolecular forces. We're going to relate the strength of their intermolecular forces to physical properties, specifically boiling point. We're going to compare and contrast different kinds of intermolecular forces, especially how they're stronger or weaker, and how that relates to boiling point. And then we're going to wrap up the day with a look at hydrogen bonding, a super special kind of intermolecular force. All right, so again, here is our essential understanding for today. Before we can really get going on intermolecular forces, we need to make sure that we know the difference between inter and intra. Intermolecular forces are forces that are between separate molecules. So I have this one water molecule here, I have a different water molecule over here, and the hydrogen bond that is labeled is an intermolecular force because it is between separate water molecules, as opposed to the covalent bond that's right here. It's within a single water molecule. That's an intramolecular force within a single molecule. And our focus today is all about those intermolecular forces. And then let's talk about boiling point. How even do we get things to boil? Well, basically, we start in a liquid form, and then these guys have so much energy that they just like pop away from the liquids. If there's not a very strong force of attraction between the liquid molecules, then it's pretty easy for these guys to evaporate and they'll just float away from each other. But if there's a lot of stickiness holding these guys together, if those intermolecular forces are strong, it takes a lot more energy to get those guys to let go of each other and evaporate into a gas. And so we're going to look at the strength of those intermolecular forces, how strongly are these molecules sticking together with these intermolecular forces, how much energy is required to kind of break those intermolecular forces so that molecules can evaporate into a gas. All right, so we have a couple different kinds of intermolecular forces, and you do need to memorize these guys. So first up, we have London dispersion forces, sometimes called instantaneous dipoles. So dipole, we're basically looking at something that's positive on one side and negative on the other side. And sometimes we have like positive on this side and negative on that side. As long as we have opposite charges on either side of a molecule, we have a dipole. So two poles. If I had a molecule that was like all negative all the way around, that would not be a dipole, it'd be mono. So we're really looking at getting things to be positive on one side and negative on another. So London dispersion, these tend to be the weakest of our forces, but we'll talk about how the sides of the molecule can actually make these guys pretty strong. And then we're going to talk about permanent dipole-dipole. This is where we do have a polar molecule, permanently polar. And then the combination of those polar molecule forces and London dispersion forces is known as van der Waals forces. Hydrogen bonding is separate from van der Waal, but interestingly, it's a special kind of permanent dipole-dipole, but we keep it separate from van der Waal. So we'll talk about all of those today, and we're going to start with London dispersion forces. So the idea behind London dispersion forces is that electron clouds are polarizable. That means that we can take an electron cloud and do things or let things happen. That's better terminology. Let things happen, where we end up with a positive and negative sides on this electron cloud. How this works is random chance. So sometimes, because the electrons are just moving around, so these electrons are moving around like crazy sauce, all of them are moving around. Sometimes, every once in a while, for a very, very, very small moment in time, we might end up with a whole lot more electrons on one side, just randomly, because electrons move kind of randomly around the atom. And if I have a lot of electrons on one side, that means that the other side has fewer electrons, which means that it's left to be a little bit positively charged. We now have an instantaneous dipole. It's a little bit negative on this side and a little bit positive on this side. Here's where the magic comes into play. Because it's a little bit positive on this side, this molecule that's nearby, the electrons that are floating around randomly all over the place, they're going to be attracted to, because opposites attract, they're going to be attracted to this partially positive lack of electron side of this next molecule. And now we have an induced dipole moment. For just a moment in time, very, very temporary and relatively weak, we're going to have lots of electrons on this side, fewer electrons on this side of this other molecule, and then we have a little electrostatic attraction between oppositely charged poles of this molecule. And when I say charged, like they don't have whole charges, it's just a tiny little bit positive and a tiny little bit negative, not even a whole positive one. And these opposites attract, and so this molecule is held together for a very, very small temporary moment in time. We induced polar molecules, kinda, sorta, but just for a very small amount of time. And these guys will stick together just a little bit. What's kind of cool about these London dispersion forces is that all molecules, polar and nonpolar, have some London dispersion forces. London dispersion forces vary a lot depending on the size of the electron cloud, the number of electrons that are in the molecule. So if we have more electrons, or more energy levels, it's actually a lot easier to polarize those clouds. And then we have greater strengths of London forces. So if I'm comparing methane here, which is 1 carbon and 4 hydrogens, we've got some electrons around, and sometimes we can have them over on one side instead of another. And there's going to be some London dispersion forces, but not a whole lot, because there aren't a whole lot of electrons. When I get up to something like butane, which is 4 carbons and 10 hydrogens, now I just have a whole lot more electrons that I can like push around. And so when I get a bunch of electrons all sitting on one side of this, just because there's more of them, we're going to have a stronger London dispersion force. And so all of these molecules, they're all nonpolar. And yet, notice the change in their boiling points. So negative 161.5 degrees Celsius. To get methane to be a liquid, we need to go all the way down to negative 161.5 degrees Celsius. Ethane with 2 carbons, negative 88.6 degrees Celsius to turn it into a liquid. Propane, I have to cool it off to only negative 42.1 degrees Celsius. And butane, super close to the freezing point of water, so just barely under 0 Celsius, we're going to have butane in liquid form. Even though it's nonpolar, we can increase the boiling points of these guys just by making them bigger. Good? Good. All right. This is kind of related also to the volume or the size of the electron cloud. More electron clouds means more distance between the nucleus. And so as things get bigger and bigger, there's just a lesser pull between the electrons and the nucleus. And so we can polarize those clouds a little bit more easily. And again, we're increasing the strength of those London dispersion forces. This one is so cool. This is such a cool thing. So the shape of the molecule can also influence the strength of the London dispersion forces. These two molecules are what we call isomers of each other. Both of them have 5 carbons and 12 hydrogens. Both of these molecules, 2,2-dimethylpropane and pentane, both of these guys have 5 carbons and 12 hydrogens. They have the same molecular mass, same numbers of carbons, same numbers of hydrogens, same numbers of electrons, and yet look at the differences in their boiling points. 9.5 to 36, even though they have the same numbers of atoms and electrons. And the reason is this: surface area. So when we're looking at a globby molecule like 2,2-dimethylpropane, there just aren't that many places where the electrons can influence each other. And so the London dispersion forces are not going to be super, super strong. However, if I have this long stretched out molecule, all of this surface area where electrons can influence each other, and we can set up those instantaneous dipole moments, there are more electrons that can move along that crazy long space. We're going to increase the strength of that London dispersion force, and we're going to have a much, much higher boiling point. So more electrons, bigger electron clouds is going to increase the strength of the London dispersion force. And if I have a stronger London dispersion force, I'm going to have a higher boiling point. And the shape of the molecule is also going to influence that. If I have more surface area, I'm going to have stronger London dispersion forces. And a stronger London dispersion force is going to mean a higher boiling point. More energy is needed to get these guys to separate from each other and go from a liquid to a gas. So now let's look at these permanent dipole moments that exist in polar molecules. So if I'm looking at something like water, so if I have water, oxygen, hydrogen, hydrogen, because of the non-bonding pairs of electrons on oxygen, and also oxygen is more electronegative than is hydrogen, we're going to have a polar molecule. The oxygen side is always a little bit more negative than the hydrogen side of the molecule, permanent dipole. Now, if I take this water molecule that is permanently positive on one side and negative on the other side, and I put it next to a perfectly non-polar oxygen molecule, so an O2, the negativeness of that water molecule is going to repel the electrons that used to be hanging out on the side of the oxygen molecule. Those electrons are going to move away from all of these electrons on the water molecule, and then we're going to have an induced dipole for just a little bit, because we're going to have a slightly positive charge left over here, slightly negative, partially negative charge on the oxygen side of the water molecule. And so we will have this induced dipole from this permanent dipole. Ooh, I can spell permanent dipole. And so there will be a little force of attraction here. This is also going to be temporary. Even though this is a permanent dipole, this force of attraction will be temporary, but stronger than if I had all just London dispersion forces. All right, so now we're going to look at dipole-dipole. If I have polar molecules interacting with other polar molecules, so looking at iodine monochloride, iodine monochloride. So the chlorine side of this molecule is more electronegative, and so it is going to be the partially negative side of the molecule. This is a permanent dipole. It is a polar molecule. And the iodine side is left to be a little bit positive. The iodine side is a little bit positive, and the chloride side is a little bit negative. There's a force of attraction between these two guys, holding them together like little magnets. So if I look at ICl and I compare it to Br2, so now I have two bromine atoms that are sharing electrons, and they can have that instantaneous dipole moment from that London dispersion force, where randomly we happen to get a bunch of electrons that just floated over on that side, which left this side of the molecule to be a little bit positive, which attracted these guys' electrons to hang out here for a little bit. And then we had that force of attraction, that intermolecular force between the partially positive and the partially negative pieces of these molecules, dipole moment. So when I'm looking just at the masses, I should think that these guys are going to be pretty similar in terms of boiling point. But in fact, they're not at all. The boiling point of ICl is 97 Celsius and bromine is only 59. And it's because the IMF, intermolecular force, in ICl is a permanent dipole-dipole, because that molecule is polar. It also has London dispersion forces. So remember that all molecules have London dispersion. All molecules always have London dispersion. But this guy also has dipole-dipole, which is going to make its boiling point way higher than this guy that has a pretty similar molar mass. So equal-ish numbers of electrons and electron clouds, similar mass, similar size, and yet boiling points very, very different. Because bromine has only that London dispersion force, bromine has only London dispersion, that we had the random electrons, which mean that this was a little bit positive, which attracted the electrons over here. And so we had that instantaneous, very small force of attraction. Good? All right. So now, thinking about London and dipole-dipole versus London only, and how big a difference we're going to make in those boiling points, I'm going to show you a couple other molecules. So 162 grams per mole, 160 grams per mole, 114 grams per mole. This guy and these guys, they both have London dispersion forces only. This is octane. Octane is here. It's only carbon and hydrogen. It's very, very non-polar. And yet, look how high its boiling point is. Why is its boiling point so high? It's less massive than bromine. It's far less massive than iodine monochloride. It has only London dispersion forces as opposed to dipole-dipole. Why? Because it's so big and it has so much surface area. Remember those couple slides ago we were talking about surface area and how that had an influence on the strength of those London dispersion forces? So the fact that we've got electrons, electrons, electrons all along this whole entire molecule, and also along this whole entire molecule, we have these huge long strips of molecules that are going to interact with each other, and that huge amount of surface area is going to influence the strength of those London dispersion forces. London only, but really high boiling point because of the surface area of that molecule. And now we're going to look at this crazy water guy. So water's mass is only 18. 18 grams per mole compared to 114, compared to 160, compared to 162. 18 is so tiny, it should have a super, super, super small boiling point. It should just want to be a gas. It's not. It has a really high boiling point. It has higher than bromine or iodine monochloride. And the reason is its very special dipole-dipole force that we're going to talk about right now. Water has hydrogen bonding. Uh-oh, my slides got stuck. There we go. Okay, sorry. Hydrogen bonding. All of that buildup. And okay, we're good. We're fine. Hydrogen bonding. It's a very special dipole moment that forms when if I have hydrogen bonded to nitrogen or oxygen or fluorine, and then we can put forces of attraction to those next molecules. So in this instance, I have NH3, this is ammonia, hydrogen bonded to nitrogen, hydrogen bonded to nitrogen. And then we're going to have a force of attraction from the hydrogen of one molecule to the nitrogen of the next. This is not just a dipole, this is now hydrogen bonding because that H is on an N and it's attracted to this next guy, an N. I can also put hydrogen bonds. I can find hydrogen bonds if I have hydrogen bonded to oxygen. So here in water, I have oxygen and hydrogen. Hydrogen is covalently bonded to oxygen. Hydrogen is covalently bonded to oxygen. Hydrogen, oxygen. The force of attraction between separate water molecules because of the bonds between hydrogen and oxygen is going to set up a hydrogen bond. If I look at this guy, hydrogen fluoride, I can, again, look at this bond, hydrogen and fluorine now, hydrogen and fluorine, hydrogen bonded to fluorine, hydrogen bonded to fluorine. The force of attraction between the hydrogen and the fluorine here is going to lead to hydrogen bonds. So I've got hydrogen bonds here, hydrogen bonds here, hydrogen bonds here, and there, because of hydrogen bonded to a nitrogen, an oxygen, and a fluorine. Hydrogen bonds do not form an any other molecules unless we've got hydrogen bonded to nitrogen or fluorine or oxygen. Good. What's amazing about hydrogen bonding is that we take advantage of it in biology a lot. So guanine, cytosine, adenine, thymine, guanine, uracil, adenine, uracil. You may have heard of some of these words before in biology class. So we have complementary base pairs, our nitrogenous bases in nucleotides, DNA and RNA. And we're setting up lots and lots of hydrogen bonds between those complementary base pairs. And it's because we have hydrogen bonded to nitrogen. We have over here, nitrogen and hydrogen again, nitrogen and hydrogen again. And then the oxygen here is a little bit polar, and then we can set up those hydrogen bonds because I have hydrogen bonded to a nitrogen. I can also set up these hydrogen bonds in proteins. We can hold together proteins with hydrogen bonds and hydrogen bonds and hydrogen bonds, and it's all because of hydrogens bonded to oxygens or nitrogens in these molecules that allows them to stick together like little magnets. Electrostatic forces of attraction. Because of the polarity of water, because of the hydrogen bonding that can happen between water molecules, we have this amazing thing, surface tension. And surface tension results from the intermolecular attractive forces, the hydrogen bondings, that are along the plane, the top surface of the sample of water. And so all these molecules are kind of sticking to each other and sticking to each other and sticking to each other. And so they build up this pretty nice solid surface because of those forces of attraction. And bugs are small enough, weigh little enough that they can balance. They don't break through those forces of attraction. Now, if we were to add more weight, if we were to add more force, instead of having the weight kind of distributed so beautifully along all those spaces, if we increase the pressure by decreasing the surface area, then the bug would go down. If we did something to break the surface tension by throwing in some salt, the bug would sink. But because of those intermolecular attractive forces holding the water molecules together at the surface of the water, the bug can stay on top. Kind of amazing. All right, so we have accomplished our objectives. We defined intermolecular forces. We related strength to physical properties. The stronger the intermolecular force, the higher the boiling point. We compared and contrasted those intermolecular forces. Generally, London dispersion is the weakest, but if you've got a giant molecule, that can actually turn into a pretty strong force. We've got dipoles, so you can have a non-polar polar dipole moment. You can have dipole moments if you've got permanent polar molecules kind of attracted to each other. And then we've of course got those hydrogen bonds. Those tend to be the strongest of our intermolecular forces. But again, London dispersion is quirky because if you've got a really big molecule, London dispersion can add up to quite a significant force of attraction. Good work today, my friends.